Welcome to Simplilearn. In this video, we are going to learn in detail about linear regression, logistic regression, and see the comparison between them. So before we begin, consider subscribing to Simplilearn and hit the bell icon to never miss any updates from us.
Let's look at an example of a common use for linear regression: profit estimation of a company. If I was going to invest in a company, I would like to know how much money I could expect to make. So we'll take a look at a venture capitalist firm and try to understand which companies they should invest in. So we'll take the idea that we need to decide the companies to invest in. We need to predict the profit the company makes, and we're going to do it based on the company's expenses, and even just a specific expense. In this case, we have our company, we have the different expenses, so we have our R&D, which is your research and development, we have our marketing, we might have the location, we might have what kind of administration it's going through. Based on all this different information, we would like to calculate the profit. Now, in actuality, there's usually about 23 to 27 different markers that they look at if they're a heavy-duty investor. We're only going to take a look at one basic one. We're going to come in, and for simplicity, let's consider a single variable R&D and find out which companies to invest in based on that. So when we take our R&D and we're plotting the profit based on the R&D expenditure, how much money they put into the research and development, and then we look at the profit that goes with that. We can predict a line to estimate the profit. So we can draw a line right through the data. And when you look at that, you can see how much they invest in the R&D is a good marker as to how much profit they're going to have. We can also note that companies spending more on R&D make good profit. So let's invest in the ones that spend a higher rate in their R&D. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, Remember that from before? And x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle. A good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from. It's called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed 1 line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across, with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your C coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1 plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1 all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. And we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumberPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT, and then Seaborn as SNS. Seaborn works with the matplot library, so you have to always import matplotlibary, and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row. That's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine, the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any two of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in two steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the third row. And in there we're going to take the label coder and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon, comma, 1 colon. All this is doing is removing that one extra column we put in there when we did our one-hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here. And I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit. Because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn .linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do X train and Y train because we're using the training data, X being the data in and Y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy X equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a y_predict variable, and we're going to put in the x test. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have y_predict equals regressor.predict x test going in, and this gives us y_predict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print y_predict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print y_predict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works, and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. And we're looking at the error. So, in the R2 score, we take our Y test versus our Y predict. Y test is the actual values we're testing. That was the one that was given to us so we know are true. The Y predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R-squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression.
Thank you for a really great session, Richard. I hope you guys found linear regression fun to learn. Now let's get into some other machine learning algorithms. Over to Mohan.
Hello and welcome to this session on logistic regression. I am Mohan Kumar from Simplilearn. What is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis, x is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected and for the number of years and when the car broke down and what was the probability. And that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variable's outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the class, the outcome rather. So for a logistic regression curve, a threshold has to be set saying that because this is a probability calculation, remember this is a probability calculation and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0 and any value above 0.5 is considered to be 1. So an output of let's say 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression because they both have the term regression in them, so it can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information so that when a new employee's information is fed based on the rating, it will determine what should be the height. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this where you're trying to find continuous values is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion. That is a no. And this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not. Yes, no, right? So there is nothing in between. And what is the employee's rating? Okay. And ratings can be continuous. That is not an issue. But the output is discrete in this case. Whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right because it looks like there will be a lot of errors. The root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability And if we plot that probability not in the form of a straight line, but we need to use some other equation, we will see very soon what that equation is, then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process, and this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening, and this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's a gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you're just plotting what has been predicted and what is the labeled information or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay. Alright, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of that entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right? Which is like the independent variable. And y underscore train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x underscore train. And since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2. So that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x underscore train, y underscore train is for the training data set, x underscore test, y underscore test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x underscore train, the shape is 1383 by 64, and y underscore train has 1383 because there is nothing like the second part is not required here. And then x underscore test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right? This is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. All right, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0. So the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1. And again, this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.